say Excel works, because this affects the other questions we're going to do, and it's just generally useful for our final exam, which will be coming up starting next week. Now, we've identified the most positive half reaction. It involves manganese solid going to manganese 2 plus 2 electrons. And literally where that happens is where the manganese solid is. And so if I take my manganese solid, it will react to form manganese 2 plus and 2 electrons. And so what I've just done is I've just drawn this half reaction in the place where it actually occurs. Like this metal, this manganese, reacts and makes manganese ions and electrons. And the electrons go through the wire. And then they go through the light bulb, they light up the light bulb, they keep going, and then they make it over here. And when they make it over here, they're going to do a reduction half reaction. Fe3 plus, which I have in my solution, is going to come up to the platinum. It's going to team up with 1 electron. And make Fe2 plus. And in fact, quite literally, I love that word, quite literally it comes up to the platinum. There will be electrons on the platinum from the other half reaction. It will pick one up, it will change into Fe2 plus, and then it will float away into solution. So I think at least one of the homework questions actually asks you to draw the half reactions where they occur in the solution. And that's what I've just done here. Okay. Jump in anytime if you have any questions.
I have a question, Professor.
Go ahead, Seldon.
So if we had FH3 plus and it kept going to completion and we get Fe2 plus, would it continue another half or redox reaction to get the Fe2 plus to another electron if it continued?
Good question. So I think your point is, well, what happens when we use up all of the Fe3 plus?
Yeah.
Then it would go to the next most positive reaction. And let's see. So you would say Fe2 plus 2 electrons going to Fe solid. That's actually at minus 0.45. And I guess I should have listed that because that could have happened. However, this reaction at 0 for a reduction would be more positive, and so that would be the next one that would happen.
Thank you.
Yeah. So, and you know, to be honest, the level, I realize this is the last material we're covering this semester. We are covering the basics. And so we won't have any questions where it says, suppose you run out of the first thing that you had. It's a good question, but just to be clear, we won't find the second best thing. In fact, in this picture, we haven't even talked about concentrations, although it is true that we assume that everything is 1 molar when we do these things, because 1 molar for aqueous species, which is what these are, is standard conditions. Any other questions? Yeah, it's a great question. Okay, so then now this is a key part of this as well. If you look at this, you're taking negative electrons away from here. And while you're doing that, you're making positive things that are going into the solution. So this solution where oxidation occurs has a buildup of positive charge. Okay. And then the electrons are being delivered over here. And this is a little harder to see, but hopefully this makes sense. First off, when you're adding electrons which are negative to anything, there will be a buildup of negative charge in here. The way to think of it, though, is you have a number of chloride ions here that are balancing the Fe3 pluses from the beginning. You take the Fe3 plus, add an electron to make Fe2 plus. You're taking away the positive charge while leaving the negative charges, the chloride ions, there. So you're decreasing the positives while keeping the negatives the same. That leads to a buildup of negative charge, even though the way you're doing it is taking away the, or decreasing the amount of positive charge. However you look at it, wherever reduction occurs, you have a buildup of negative charge. And if you can imagine that you've got a negative place over here and a positive place here, so you're trying to take electrons away from someplace that's positive and move them to someplace that's negative, the electrons are not going to want to go there except for one thing. And that one thing is the salt bridge. The one thing we haven't talked about, that's the salt bridge right here. And the salt bridge is filled with a saturated solution of some salt, some ionic compound that dissolves. Oftentimes I draw them as potassium chloride, could also be potassium nitrate, could be sodium chloride, anything that really dissolves in water, totally soluble. But what happens is there's all these ions, and so we could think of it like this. So K plus Cl minus K plus Cl minus K plus Cl minus all the way over here. There, something like that. So this is a saturated solution of potassium chloride. And I guess there, the whole salt bridge is filled with it. Let's zoom in even more. Good. And what happens is the salt bridge transports ions to maintain charge neutrality. So here's the full picture. Oxidation occurs. 2 electrons are produced and they go through the wire. Now there's a buildup of positive charge in the solution because we've just created a manganese 2 ion. That or some other manganese 2 ion that's in solution then goes into the salt bridge. And on the other side, a potassium ion gets kicked out of the salt bridge, or really 2, but we won't worry too much about the numbers here. But something positive comes in here, and something positive comes out the other side. Because ions, the way that ions, some come in here, and then it kicks out a corresponding number of the same charge on the other side. And then the electrons come over here, And because there's positives here, the electron can then come and become Fe2 plus, and charge neutrality is maintained. So the way that this works is the electrons go through the wire, the ions go through the salt bridge. Both are needed to maintain charge neutrality. No salt bridge, no electrons going through the light bulb and lighting it up. And I think that's basically, and it certainly looks like it because it's messy enough, I know, but that's basically how a voltaic cell works and how batteries work. And the only thing that's different between this and a battery that you would put into a cell phone is that the cell phone doesn't typically have liquids. It typically uses solid materials, although it's complicated. But that's basically how a battery works. It moves electrons through a wire, and those electrons are created from an oxidation half reaction. They arrive over here and do a reduction half reaction, and the cell potential is positive. And the last thing I'll say about this, and then this is, I know, the longest problem ever, but if we wanted to know the potential of our cell, it would be add up the oxidation and the reduction. 1.18 volts plus 0.77 volts, and I get 1.95 volts, which would be how much voltage you could get from this voltaic cell, which is a type of battery. And I don't know if you know this, maybe you do, probably you do. So well, let me ask, does anybody know the voltage for a AA or a AAA battery? You could look right on it, eh? Because it says it right on it. Well, AA's, AAA's, single A's? Do they even have single A's? C batteries, D batteries, so many batteries that we use are each 1.5 volts. So we're in the range of a real battery here with what we've just created. Although I know it's not very practical to carry around beakers of solution, but we're talking about things that we could, so we're talking about batteries not that could actually help us in electronics, but we're talking principles. So
excuse me, Professor.
Go ahead.
Were you talking about the A batteries?
Yes, AA batteries, A batteries.
Yeah, so what's the difference between the A, the AA, and the AAA?
Size.
Oh, okay.
Yeah, they're all 1.5 volt batteries. I think C batteries and D batteries as well. The only thing is size. So if you want to have something that's really small, like I just changed the batteries in my Roku remote a couple of days ago, you want AAA batteries. If you have a flashlight that you want to last for a long time, then you might get bigger batteries. If you remember, so some of those flashlights have some pretty big batteries, those D batteries. And batteries, by the way, huge, like so many more uses for portable electronics than there used to be. So much more desire to make better batteries. Of course, they're making batteries that are lithium batteries that are much longer lasting, can be recharged. And there's a lot of details about batteries. We're just barely scratching the surface. But all of them work on this principle. You have one material that gets oxidized. It creates electrons. Those electrons power my Roku remote, my cell phone, my laptop computer, then they come to someplace else, they come back to the battery and do a reduction half reaction. So the principles are solid. Any other questions?